Number 8, we're going to draw a picture of this cell. So we work from left to right, and this is our anode. And oxidation occurs at the anode, and this is our cathode. And reduction occurs at the cathode. So on the left, I will put my anode stuff. So I should have a platinum wire. So this is platinum. And I also need my mercury liquid. I need Hg2Cl2. That is a solid. And I'm going to need KCl. Now this looks an awful lot like a calomel electrode. And then I'm going to have my voltmeter. Use a V here. I'm going to put a minus sign on that side. I'm going to put a plus sign on this side. And in my other beaker, I have my cathode. So I'm going to have my zinc chloride aqueous solution. And then this is zinc. So we'll beef it up a little bit. Call that zinc. Make it some liquid. Then we also need a salt bridge. So I'm just going to kind of draw my salt bridge like this. And then I have my cell. Now it's sloppy because I'm just not artistic in any way, shape, or form, but that's what we have. Now we are asked to write the reduction half reaction for each half cell. So for the cell on the left, we have Hg2Cl2 solid plus 2 electrons is going to be in equilibrium with 2 liquid Hg plus 2 Cl minus. So that is for the anode. And for the cathode then, we will have zinc 2 plus and 2 electrons in equilibrium with zinc solid. C, for particular conditions, the zinc electrode has a potential of 0.75 volts, negative 0.75 volts, and the platinum electrode has a potential of positive 0.25 volts. So in which direction will the electrons flow when the zinc and mercury are connected by a wire? Electrons always flow from less positive to more positive. So given these conditions, electrons will flow that way. So given these conditions, this is actually the anode, and then this is the cathode. As the cell is written, we usually put the anode on the left. And I erased that before I read the remainder. Write the net cell reaction combining the correct oxidation and reduction. If the zinc is going to be oxidized, the zinc is going to be the anode, then we need solid zinc on the reactant side, and we need the zinc ion on the product side. So that also leaves our liquid mercury on the product side and our 2Cl minus, because we are going to reduce the Hg2Cl2. Now let's go down to number 10. Suppose that the concentrations of sodium fluoride and potassium chloride are each 0.10 molar in this cell. So these are both 0.1. Using these half reactions, calculate the cell voltage. Now, if I was going to ask you this question, I'm not going to give you the half reactions. I do expect you to be able to pull out the half reactions. So we are going with AgCl, and they've even balanced it for you. That's very kind. 2Ag plus 2Cl minus, and then we have PbF2, 2 Pb, and 2F minus. So before I calculate the cell voltage, if I was going to ask you this, I would ask you, I think I would stop here. I don't think I'm going to ask you about the KSP in a question like this, because what I would do is I would give you this cell and ask you to calculate the cell voltage. So we need to use that Nernst equation. So the E is going to be equal to the E naught of this cell minus 0.05916 over N times the log of the Q value. So we need products over reactance. So I brought in our half reactions here, and I'm looking for the silver and the lead. So here are the half reactions. Here is the silver at 0.22, and then it continues. And here's the lead reaction that I need, negative 0.3505. So to find the E naught value, I need the E of the cathode minus the E of the anode. Well, the anode is the one on the left in the cell notation. Let's go back over here. So the lead is going to be the anode. That means the silver is the cathode. So I need 0.22 minus a negative 0.350, and that's going to be my E naught. So the E naught value I get is a positive 0.57 volts. Now, how many electrons are being transferred here? Well, because it was balanced for you, the N value is 2. We have 2 electrons that are being transferred. Now, which are the products and which are the reactants? Well, let's set this up as a balanced equation with oxidation being shown and reduction being shown. So that means I need to reverse this one. So PB. So now I combine. So my balanced equation would look like this. I'm going to leave the electrons off because they cancel out from both sides. So I need the concentration of the products. Well, the problem told us that both of our fluorine and our chlorine are going to be at 0.1. But in our balanced chemical equation, they are also both going to be squared. So I have 0.10 squared divided by 0.10 squared. And because this is a 1, the log of 1 is 0. So our E value is going to be 0.57 volts. Now, what happens if those aren't equivalent? What happens if, say, our fluorine is, I don't know, let's pick something. Let's say the concentration of fluorine is going to be 0.10, but the concentration of chlorine is then going to be 0.001. 010. Let's do it that way. So I still need products over reactants. Products, my chlorine, so I need the concentration of chlorine 0.010 squared over the reactants. Concentration of fluorine squared. So now I have something a little more to calculate. So when I calculate this log value, this works out to, and I'm just going to write everything down. So this is 57 divided by 0.5916 over 2. This is the log of 0.01 now. So we get a negative 2. Then I end up with a new E value of 0.62916. We have to check our significant figures, and we would probably be rounding that to 2. So 0.63 volts. So you see, as we change these values here, the E value is going to change as well.